Thank you everybody who joined today. Today's session is from Dr. Jason Larkin. Dr. Jason is from Carnegie Mellon University, and today's topic is evolution of quantum approximate optimization algorithm based on the approximation ratio of single samples. With that said, I'm going to pass it to Dr. Jason. Dr. Jason, go ahead.
Okay, thanks. All right, so I'm going to keep the chat visible and also the Q&A. I guess there's two different ways of asking questions. You can use either one if you want. Let me make sure I have the chat open here. Okay, and the Q&A. All right. Okay, so yeah, so this talk is called Evaluation of QAOA, and I think I want to start off by first saying, like, please give me any feedback from the audience about the rate of at which I'm going or the information what I'm talking about or something needs to be clarified. Because I tried to basically take, there's a paper link in the meetup link, which is an archive paper that we have submitted. And so I'm basically going to explain that paper. But you know, if I'm going too much in detail or not in detail enough at any point, just let me know. Okay, so I'll let you know what QAOA means if you don't. But first, let's say like the overarching goal of the research I do is to try and figure out where quantum advantage is going to be found for practical applications in quantum computing. So when I talk about evaluating QAOA, I mean for what? For quantum advantage. And then there's an additional constraint here where I'm particularly interested where there might be advantage in the NISQ era. So that's the noisy intermediate scale quantum computing era. It's the era that we're in right now, and we'll probably be in for the next 5 years or so, maybe 10 years. And so like this era is sort of characterized by a qubit count number that we might expect between 100 and 1,000 maybe, and maybe fidelity is in this range here. It's not so clear what 1 and 2 qubit gate error rates will be or what the architecture connectivity will be, because there's several different, you know, quantum computer manufacturers out there right now, and all of these different parameters here are variable and then some. And then the additional question is, for this NISQ era and for short depth and noisy quantum computing, short depth circuits, what is the complexity theoretic guidance for quantum advantage versus a classical alternative? So within this NISQ era, there's at least 3 major focuses on applications, and that's in material science, combinatorial optimization, and machine learning. And I would think that probably like past, you know, past presenters have already talked maybe about all 3 of these, I would imagine. So I'm going to focus on one of these, combinatorial optimization, because it's the focus of the paper that I'm basically summarizing here. But these are 3 at least applications, at least 3. Okay, so in terms of practical applications in combinatorial optimization, I'm further focusing on this problem called MaxCut, which actually has practical applications in a bunch of different domains, at least the ones I have listed here, like in community detection. Oh, I'm sorry, actually, this is the wrong one. I realize I'm not giving you the examples of MaxCut here. I'm giving you other combinatorial optimization problems, so that's my fault. But I could give you a long list of them. One nice visualization of the use of MaxCut in a practical setting is on the right-hand side. This is like a wiring schematic for a VLSI. And then MaxCut can actually be used on this problem to produce some sort of like more optimized version of the circuit. I forget exactly what's going on here, but this gives you an indication of where you use this problem in practical settings, and there's a bunch of other ones too. It might also give you a sense for, like, at scale, what are practical application problem sizes like. On the left is a description of this MaxCut problem for a very small graph. Basically, the problem is to take a graph, which is just a set of nodes and edges, and then figure out a labeling of the graph such that that labeling defines a cut of the graph. And then you want to maximize the value of this cut. So it's actually a very, very simple problem, but it's an NP-hard problem to get this maximum cut. But instead of trying to get the maximum, you can actually pretty efficiently get approximate values, pretty good approximate values to this problem in polynomial time. So this will come up later in the talk. I'll talk about, you know, when we do benchmarks to try and evaluate or to try to determine quantum advantage, this will come up again. And then there's another link here on the screen. It's a nice talk about the MaxCut problem itself. A really great, sort of description of the problem, description of classical algorithms to solve it, and the nature of its NP hardness and approximatability, which are very important. Let me just check and see if there's any questions in the chat or anything so far. I don't think that I can see my chat window right now. It's like not visible. So you might be chatting to me. I can't hear you. One of the panelists, if there's some chats, questions, let me know. I want to keep going. Okay. So the question of this research was to look at for, in this NISC era, what people are looking at is what's called quantum variational optimization. And so the defining features here are we want to do optimization, we want to do it variationally. We're to follow some procedure, some variational procedure to accomplish this optimization. That's the basic ingredients. So this talk is about QAOA, but QAOA is just sort of one flavor of this variational optimization. There's another popular method called variational quantum eigensolver, VQE, and it gets used a lot in the material science domain. But they're actually in the same sort of variational family. They just differ. So here's some references here if you wanted to read up about QAOA. References, the differences, for example, between these two, VQ and QAOA, which are kind of related, and what are the differences between them. This reference is a good one to distinguish. And like I said, this QAOA will be the nature or the subject of this talk and of the paper that I'm basically summarizing. Okay, so what is this QAOA? So QAOA stands for Quantum Approximation Optimization Algorithm. And the point of this algorithm is to produce a state here called gamma beta, which either solves or approximately solves the, did you share the slide? Oh, you want me to share the slides like by email? And do you want them shared now or can you wait till after? Because I think the answer to either is yes. But I'll keep going while we think on that one. So the point of this algorithm is to create or to produce a state gamma beta, which basically represents the solution or approximate solution to your problem. So you accomplish this, the production of this state gamma beta. Cool. You accomplish the production of this state gamma beta by a sequence of unitary operations on an initial state, here the plus state, basically a superposition state. And so the point of this algorithm is to construct this variational circuit. It has now these variational parameters inside of it, gamma and betas. And the goal of a classical optimizer, which is making measurements on the quantum computer, making measurements and then in an outer optimization loop, modifying these variational parameters gamma beta to try and improve the quality of the solution to the problem to accomplish the optimization. So it's a hybrid. You need a quantum computer, a classical optimizer, optimization scheme. And these two things work together to try and either to solve your problem or approximately solve it. So typically the focus on approximately or on solving the problem is to look at the expectation value from this state. So we want to produce a state gamma beta, and then we take the expectation value, which with the C operator, which is basically the cost function, the thing that defines your problem. So this method is quite general. It's defined basically by these variational parameters and the particular cost function you're trying to optimize for. So it makes the protocol very general, and you can implement a wide variety of optimization problems with this. So for MaxCut, this QAOA problem ends up looking like this. So the particular operators that we were talking about before, this B and C, they take on particular specific values with this MaxCut problem coming directly from the cost function that defines that problem. So for MaxCut, we have C here is now this quadratic cost function. Here we make a change of variables from the classical problem where you have some coloring or labeling of the nodes and that takes on plus or minus 1. Here we can replace that in the cost function in the quantum mechanical version with these poly Z operators, Zi, Zj. So you have a sum over all the different or over all the edges in the graph. And for each edge that exists, we'll implement one of these poly Z operators, Z, I, Z, J. And so if we wanted to do a different problem, a different kind of optimization problem, we would change the cost function C here. And then B are just a sequence of single qubit rotations parameterized by another angle beta. And so basically these angles gamma and beta, they're there to be modified to try to better optimize the problem or produce a better solution through the state gamma beta and the measurements of the expectation value. Okay, let me see. And yeah, maybe for panelists, because for some reason I can't get like my chat to be up on the screen at the same time as the Q&A and the slides. Let me know if there's chat questions. I'm not able to directly monitor them. Okay, so in addition to the cost function defining this problem, also what defines this the quantum circuit that we'll need to generate is the particular structure of the graph itself that we're trying to solve the MaxCut problem on. And so this where it comes in now. The application MaxCut's important, the sort of the structure of the algorithm, the circuit and so forth, but now also the graph type is too. So in the paper, we looked at a number of graph types, in particular because we needed this variation to determine if there was variation in performance of optimization, but also because we're limited at simulating quantum computers right now in a sort of very narrow range of node sizes, like up to maybe 32 or 36 nodes or something, until simulation techniques become not possible. So although these are a variation of graphs on the left that we use in the paper, so random K or D regular graphs where the graph now has random edges, but a bounded number of them. So let's say each node would be connected to 3 other or 4 other or K other nodes, but this would be done randomly. Similar to that type of graph is Erdős-Rényi graph, where you basically have, for any given node, it has a certain probability of being attached to other nodes. And in this case now, that graph type would have an unbounded number of degrees in its structure. So you sort of lose structure going from D regular to Erdős, among other things. And then another interesting graph type is if you have the MaxCut problem, where instead of just having node connections or edges, you have weights between the edges as well. A particularly interesting graph type is this one. And then also to keep in mind, because this will come up later, on the right are these real world graph problems. I know graph problems. Yeah, I should have clarified, sorry. So the way this QAOA problem works is basically for every qubit, for every node, you need a qubit. So when I say number of nodes, basically the number of qubits dictates the size of graph you can run on the processor, the chip. Although not exactly, but that's a good rule of thumb. And the number of edges will essentially end up dictating the circuit depth. So the more edges you have, the more gate operations you're going to need to execute. Does that help? Okay. So yeah, the only point I want to make here is that, we were really limited in the paper on the left to sort of a selection of graph types and sizes, but because of computational limitations. But sort of in the real world on the right, we have really graphs up to, hundreds of thousands of nodes and edges and more. So this is particularly challenging for this problem in quantum computing, is like waiting on quantum computers big enough or figuring out ways of representing graphs on them that can compete with these sort of, practical scale graphs. Okay, so this slide's a little bit cluttered, but basically once you have once you have your problem MaxCut and you have your graph type, then this is going to produce some circuit, some quantum circuit that you're going to need to then schedule onto particular hardware. And so right now we have sort of like we have a few different hardware connectivity types, but one type would be like IonQ's architecture, which is all-to-all connectivity, versus like Google's Sycamore, which has a nearest neighbor connectivity, and IBM's, which is pretty close to nearest neighbor connectivity, and also Rigetti. And so, but this is still a problem you have a high-level description of the problem, QAOA, this variational form, the circuit it produces, but then that circuit also needs to be further transformed down to the particular hardware. In the paper that we did here, we did a very simple mapping, scheduling basically of the circuit. We didn't take into account like noise adaptive stuff. Basically, we're trying to make this sort of analysis on ourselves easier. Oh, the other thing here being that our simulations in this paper are noiseless. So there's a whole other layer that you need to consider if you have noise, or if noise is significant in terms of the scheduling of these circuits to real hardware. But that's a difficult process itself. And actually, the research we're doing now is working to include noise modeling and also push this work onto bare metal. So that's something that we're doing right now, but it was still challenging when we did the work. And so at the end of the day, what we're going to need, we need some kind of scheduled gate sequence or gate schedule to end up computing some wall time of execution. So we're basically using here a sort of very simple model of the hardware. So we can get a ballpark estimate on, when we go to do benchmarking, how fast would these quantum processors be executing and solving these optimization problems. And there's plenty of refinement that you can do on this. This is just to try and get in the ballpark. Okay, so what ends up being the challenge for these variational optimization methods is that basically it ends up being hard as, well, I guess I didn't describe this well enough, but these variational methods, their form is basically this big block, which are these two operators B and C, which we just discussed earlier, where it's basically the cost function and some single qubit rotations. And then you can have P number of these blocks. So this QAOA optimization scheme, you can increase P, the depth of the circuits. And that also increases the number of variational parameters. So for P equal to 1, you'd have like 2 parameters, gamma and beta, to modify to try and solve the optimization problem. But as P grows, you'll have 2 times P number of parameters. So the number of parameters grows linearly, but fairly soon it gets very difficult to find the optimized variational parameters within this landscape, this variational landscape. So on the left here are some plots of what the expectation value looks like for different gamma beta, for different values of gamma and beta. So on the left-hand side here is beta, on the y-axis beta, on the y-axis beta, x-axis gamma. And what this plot shows you is that there's huge variation in the value of the cost or the value of the expectation value over the gamma beta landscape. So if you were just to pick a value of gamma beta randomly, you would actually get a very poor solution to the problem. It's these very particular sort of concentrated regions where you have good gamma beta. So for 3 regular here, you see these 2 locations here. Actually, you see some symmetries within this landscape that you could probably use to further reduce the landscape and the number of the locations of minima. And then as the graph structure changes, so like 3 regular, 9 regular to Erdos graph types, you start seeing a concentration of the optimal regions of gamma beta. And you can imagine as you project up to higher P, from P1 to P10 or 100 or whatever, that it's going to be very hard to search through this landscape to find these optimal regions. What we would like, and what is possible for some graph types, we would just like to know what are these gamma beta, what are their optimal values a priori. That would be great. But the results so far, that you can only determine those for a limited number of graph types. And then in some cases, you can determine what gamma and beta are optimally, but it might cost you, let's say, exponentially in P to determine them. So you kind of are fighting a losing battle. There's no easy win there. Okay, so what I'm showing you here is the expectation value. What does the landscape look like? Where are the good values of gamma and beta? And they concentrate. And they're less concentrated if the graph structure is different. So they 3 and K regular versus Erdos and random weights and complete graphs. Okay, so what we did in our paper is, we tried to improve from sort of off-the-shelf local optimization. How can we find better gamma beta? Because it's probably going to have a large effect on the performance. Okay, so let me try and demonstrate here what happens basically. So we can take this gamma beta that we find as we search through this landscape of different gamma beta, and we can compute the expectation value. This is basically what you do when you run the circuit. You pick your gamma beta parameters and you specify your circuit is specified. And then you run your quantum circuit. You make measurements. Well, when you make measurements, you're going to get a distribution of outputs, of bit strings. These bit strings correspond to a labeling, a coloring of the graph, which has some particular cut value. Okay, so what we did in the paper is we ran simulations where instead of just representing this expectation value, we looked at the distributions of the output of measurements from these simulations. And from that distribution, you can compute the expectation value. And this is also how we got the optimization. But there's a lot more information contained in the distribution itself than just in the computation of the expectation value or the average, basically. So what we have here is, if you look in this blue, this is the distribution. If you just pick a gamma beta at random, so like let's say here in this plateau region or something. So this blue distribution, its expectation value would be somewhere here. And so that cut value would correspond to something that isn't much better than random guessing, basically. So this green distribution is the plus state. So no gamma beta and no variational parameterization of the circuit, just the plus state. So blue is sort of like only a marked or marginal improvement over random guessing, more or less. And then optimal values of gamma beta, let's say over here in this minima, produce not only good expectation value, but also high overlap with the maximum cut. Okay. So what we did was we ran these simulations and then we produced these cut distributions, which you can derive directly from the state gamma beta, basically. And then we asked the question, if we find the best gamma beta that we can throughout the whole space, what does that mean for performance? How much better is that, let's say, than just random guessing, or even local optimization? Okay, so what we did in the paper was specified basically an expected number of shots metric, or an execution time, or what you would call a time to solution. So we took those distributions I was showing you, unoptimized or random guessing versus what the optimized gamma beta look like, what they yield. From that, you can basically compute its cumulative distribution function. And from that, you can produce an expected number of shots before you can observe a cut quality, let's say R, above a certain threshold. So R here is just, let's take whatever cut value you measure and divide it by the maximum cut. And so this will just form a ratio R, which varies between 0 and 1. So it'll have a maximum value of 1. And in general, it'll be less than 1, maybe 0.8 or 0.9 or something like that. So, and then if we couple this together with the simple model we had for the circuit and the hardware, all-to-all or nearest neighbor connectivity, then we can put these two together and come up with a wall time and execution time. How fast did this thing solve? How quickly did the quantum processor output a solution of a given quality? Okay. So maybe some more comments on QAOA performance. So QAOA has a connection with the adiabatic quantum computing. Basically, you can think of QAOA like a characterized version of quantum annealing. And then there's also a guarantee in the P go to an infinity limit that you can find the optimal solution, of course, in the infinity limit. So okay, that's great. There's a limit there, but that's infinity. And the performance in the intermediate P range is still being understood. So we looked at it. There's tons of other papers, and it's an ongoing effort to understand what is the performance of this algorithm. What was very interesting early on was that Eddie Farhi, the guy et al., and his other authors that came up with the algorithm, it demonstrated an approximation guarantee for the problem max3 lin2, which is related to MaxCut, for p equal to 1. It gave a better performance guarantee than classical algorithm. But then soon after that, people found a better classical algorithm than quantum. So now the situation is still being determined. So now it comes back to this variational parameter, finding good variational parameters. What are the different methods to try and find these things? And it varies. It varies from, let's say, local optimization. Well, first, you could just randomly guess. But as I tried to show you, that's not a very good strategy. Then you can try some sort of local optimization, either gradient-based or non-gradient-based. Oftentimes, non-gradient-based optimization works really well, especially for noisy devices, because gradients are not well behaved. But what we did instead is we used a combination of a local optimizer with a global sort of optimization manager, which is capable of more efficiently selecting regions of this optimization space to search for minima. And this was called APOSM, Asynchronously Parallel Optimization Solver for finding multiple minima. And we found that this introduced a large speed up in finding these minima over just a local optimizer. Although we did use a local optimizer with this APOSM, APOSMM. Okay, so this is really this is the hard part, figuring out where these good gamma beta are. Okay, so this plot might be a little difficult to follow, but basically I said that the landscape is the problem, finding good gamma beta. So then what we were demonstrating, or tried to demonstrate here, but it's not that clear, it's the weak point of the paper, is in the middle plot, this is the distribution of gamma beta over, let's say, a given graph type, let's say 3 regular or something, but like, 100 instances of that graph type. So for a 3 regular graph at 12 nodes, there are many realizations of a 3 regular graph because the connectivity is random. So you have to sort of instantiate a bunch of instances and then do some averaging over those to see how do the parameters vary over even different instances of the same graph type. So what we found was that at least some evidence that parameters seem to cluster. That is, when you have these different instances and you send these solvers, or I'm sorry, these optimizers out to look for good parameters, the optimal parameters that are found seem to concentrate, at least somewhat. Not the most convincing evidence, but this effect has also been seen in other papers, references, and we reference a bunch of them. And so at the end of the day, on the far right, what you can basically do is if you just subtract the distributions produced. So in the middle plot, there's V12, that means 12 nodes, V16, 16 nodes, V20, 20 nodes. You just subtract the distributions, you'll see that basically the clustering of the parameters, it changes less for the 3 and the 9 regular, the D regular graphs, and it changes more for the Erdos and the random weight graphs, which I think basically shows you that structure is playing some role in whether or not the parameters cluster. But the way we judge whether or not this clustering works is we're going to use those train parameters in the further plots to then use those parameters and not do any optimization on larger graphs and see if those train parameters from small graphs are good enough to get you good performance. And that's something I think that
I think we lost you, Dr. Jason. We lost your audio.
Am I still here?
Can't hear you anymore.
Oh.
Yeah, okay, you're back.
Am I back?
Yeah.
Okay. Okay. Yeah. So so I think this is a common scheme throughout these variational methods. It's basically, can we basically train, can you get rid of the overhead of this whole process, finding these good parameters by just reusing them from smaller instances or similar instances or whatever. And so we did that in this paper, and other people have done it and shown that it's, at least in some contexts, it works. Okay, so these plots are showing basically for different graph types. Let's have a mouse. The same kind of plot I showed you for that 3 regular graph, the difference between random guessing or random selected parameters versus optimized ones. And then we can use that, that time to solution definition that I mentioned to go from the probability of measuring a cut to now the expected number of repetitions of the circuit you would need to execute to get a cut of a given quality. So that's R. So what this is showing is that basically in the orange, if you run the run the quantum circuit with these optimized parameters, you would get much higher cut values in much less time, basically, which is what you want. It's what this whole scheme is supposed to be doing. But then also this protocol is affected by the graph type and the structure. So the same kind of behavior. You have 3 and 9 regular, deregular graphs, which have the most structure of the graphs that we're looking at. And you see its ability to produce basically these distributions with high overlap with the maximum cut, whereas it gets harder as the graph structure changes. And you can see that manifest in these expected shots where it begins taking more wall time basically to achieve a given quality versus, let's say, these 3 regular graphs. And so that's the point. But overall, you see a big reduction versus, you know, random parameters, like maybe 2 orders of magnitude in wall time. And so that's huge. Okay, yeah, so basically this plot is showing you the whole point of on the plot on the right, the previous plots was to show how much wall time you can save by doing training and finding those optimal parameters. What we're going to look at next is whether those parameters, whether they can be transferred to larger instances, because that would be a huge savings in performance. The other thing that's now on this plot is, in addition to the previous plots, now we're in wall time because I used those circuit models to come up with an estimate for how much time they would take to execute those circuits. And now you have orange and blue, or light orange, orange and light orange, blue and light blue. And those represent the nearest neighbor versus fully connected hardware. So it's actually not that much difference between the two. There's like an overhead of a factor of 4 or 5 or something like that. But there's a huge, like a 2 order of magnitude difference in untrained versus trained. And then also what we have now is 3 different classical solvers. So within classical algorithms, you have exact solvers. So in general, they're going to give you the maximum cut, but they're going to take exponential time to do it. Then you have approximate solvers. So they're going to produce cuts of at least a given quality. And in this case, there's an algorithm for doing this for MaxCut called Williamson, which is based on semi-definite programming. And it also runs in polynomial time. So what also is on this plot, so the exact solver is AK, it's in that purple dot. And GW, this approximate solver, is in the green and the red. And this blue scattered dots are from a heuristic solver. So heuristic solvers don't come with any guarantees. You have to judge them empirically. And that's basically what we're doing on this plot. So we have our untrained and trained QAOA results for MaxCut, how much time it's taking to attain a cut of a given quality R. And then now we have all a big smattering of the 3 major classical solver modalities, exact, approximate, and heuristic. Now, the data that's on here is kind of interesting, but what we should keep in mind is that the graph size on this plot is like 16 nodes, okay? So again, that comes in with how difficult it is to simulate quantum computers, and points to getting availability to real quantum computers. So the results are interesting. Basically, it shows QAOA is in the ballpark, at least under the assumptions we made, right? And we made some pretty strong assumptions, pretty favorable ones, I would say, with respect to quantum hardware. The training is a huge benefit, and the QAOA can be made competitive in this context. But the big question comes down to the assumptions on the hardware performance that we made. Okay, and so, you know, one of the major assumptions we made here was no noise. It made things a lot easier in many ways, but it's missing a real situation, real noise. So our results are noiseless. Recent work, in the middle here, I have a noise model equals depolarizing. So a depolarizing noise model, if you all are familiar with it, is pretty standard. It's not a full description of real noise, but it's at least a good approximation. It's useful. And this is like the depolarizing, dephasing T1, T2 model. What was shown recently was that basically, in this paper is in the middle, was that although noise, when you add to QAOA, it basically acts to flatten the gradients of the landscape, the optimization landscape, but the general features of the landscape don't change very much. And so we're doing work now on that to determine if that's the case or not, and then also trying to get on bare metal and do experiments there. On the far right are the results from the QAOA Sycamore. So that's QAOA on the Sycamore. The Sycamore is it's like 53 qubits. I think it has fidelity of like 0.994 or 0.994. But as you can, and I think these results are for 23 or it might be 12 qubit graph. But anyway, the point is on this plot, you can see clearly on the far right in the experiment, the optimization, the energy landscape, expectation value landscape. definitely has additional features beyond just a flattening of the gradients, right? So what's interesting is to consider in the results I was showing you, even for like a 16 node graph, we're going to have very or pretty deep circuits, like maybe for certain graph types, hundreds of gates or 100 gates or something like that. And I think that, we need hardware to get a lot better just to be able to run those graph types, those graph sizes. And of course, they're not even really that interesting. 16 nodes is not that interesting of a graph. Not just about any graph you make it's hard to make interesting at that size. So yeah, talking about what the current coherence times are, fidelities of these devices. I think most of the work I was showing, and even up to this point, is you really can't run on those devices. The other interesting thing to consider is the cost to run on these. I recently learned that the Brocket, AWS's Brocket, has both Rigetti and IonQ. And if I recall correctly, these are the numbers per dollars per shot. So they charge by a number of times a circuit's executed. And up to this point, maybe I didn't make clear the budget, but you basically need something like, for statistical averaging, you need to run these circuits like 1,000 times, let's say, and collect measurements. And then in the outer loop, in the optimization loop, you might need to do that 100 or 1,000 times itself. So you have 1,000 times 1,000 total number of shots, and then you end up at a number here like something like the training we did or the experiments we did in simulation might have cost $100,000 on these devices that we're seeing now. So this makes everything pretty challenging. Okay, so yes, in terms of this train performance, so we try to train these parameters at small graph sizes, and then transfer them, like use them and just execute those circuits for larger graph sizes with the same variational parameters. But don't do any optimization, don't do any training, just run them and see what you get. So that's what we have here on these plots. So this is 3 regular, 9 regular, Erdos. Each of these, so this is 20 vertices, 24 up to 32. These are all have been produced by executing the variational parameters trained from the V16, from the small graph size. So the question here is, can you keep this up? Can you continue this transference, or do you need to do a retraining at some point? Or these are all things that need to be looked at. But even these graph sizes, 32, is not very interesting from a practical standpoint. We really need to get out into some asymptotic region to start judging the performance. There's nothing really being judged here. Just interesting that these performance results are all in the ballpark, and QAOA is quite competitive. And it's also like the other solver solution techniques. Generally speaking, the problem gets at least exponentially hard with R as above a certain value of R. Okay. Okay, good. So basically, what we showed, what I just showed you in the previous slide, was more or less the conclusion in the body of the paper. And so the conclusion is something like, we tested the training of these variational parameters at small instance sizes. The transference to larger sizes seems effective. That's a huge savings in overhead and total wall time to try and judge the performance of this QAOA against classical solvers. And then the fundamental questions are, can this training work beyond just 32 nodes? Can we go up to 64 and whatever powers of 2? We have to do a retraining. How does noise affect this whole process? I mean, overall, it affects it by establishing some kind of coherence window, out of which you basically can't run graph sizes of that size. So that's going to dictate graph size. But then the question is, can you maintain this kind of training, or does the landscape itself remain, more or less the same structurally when you add noise? Probably it will up to some point, right? And then also, is there a method to test transference from, let's say, a depth of P4 to P8 to P16 and so forth, as you try to improve the quality of the solution, and what's optimal in that space? So you have a few different variables to work with here. I think we're going to have to leverage all of them to try and figure out what's most performant. Okay, so in the appendix of the paper, I have a set of of results for graph sizes with graphs of size that are practical. So now we're talking about graphs like 100, 1,000 nodes and larger. And I showed you before, even at the very largest scales, the practical graph sizes will be 100,000 nodes or something like that. So just in the appendix, what we see here is you really see the behavior of these different solver types, especially from classical. So on the right, there's two graphs for 3 and 9 regular graphs, random regular graphs. And inside the graphs are solution types. And the purple is AK, the exact solver. So this thing scales exponentially. So this is a semi-log plot. The green and the red are the Gomez-Williamson approximate solver. And they eventually they scale polynomially. But because of a large overhead between it and the exact, it's going to take a while before the exact solver overtakes them in wall time, but it will, somewhere around 400 or 500 nodes. And then in the blue, light blue, silver, you have results from the heuristic solver, where you just tell the heuristic solver, here's some computational time, go and find the best solution you can, and then you can judge what quality solution it found. As you demand a higher quality solution from the heuristic, you can get the heuristic scaling to begin scaling exponentially. So as you raise so this MaxCut problem is an NP hard problem, and but it has its NP hardness does not occur until a very narrow window away from the maximum cut, or of R value of 1. So what you can basically do with the heuristic is you can demand higher and higher quality and change fundamentally the wall time scaling of its performance. And then all of these exact, approximate, and heuristic results are all sensitive to the graph type. So 3 regular on the top is 9 regular on the bottom. Some general features are the same, an exponential scaling for exact, polynomial scaling and approximate, ability to transition the heuristic to a exponential scaling. But sort of a lot of the overhead and overall constants have changed. And this is true in general of this MaxCut problem. A lot of the results depend significantly on the graph type. Okay. So, and then going back further, that's just sort of the graph types that I was able to focus on in the paper. In the real world, there's a whole bunch of other graph types, graphs of up to size 100,000 nodes and maybe even more, and different densities, sparsities of the graph, how connected the graph is. And so really in judging this QAOA on this MaxCut problem against classical, I think you're going to need a lot of benchmarks, and you're going to need them across this range of sizes and instance types to determine advantage. Right. So you need all these 3 modalities from classical: exact, approximate, and heuristic. You need this range of real practical instance types. And then the recipe for this MaxCut problem, which we can run QAOA on different combinatorial optimization problems just by changing the cost function, the variational form maybe. But this whole study is basically a recipe for how you would judge any of CARPS 21 or many other different problems like this. And so, yeah, so the question is, when will quantum hardware exist that are capable of not just executing these sizes in this training that I've demonstrated, but also demonstrate some quantum advantage, some improvement in quality or wall time or both, like in the results that I was showing you previously. So what's interesting is in trying to figure out when will we have some devices that can run this stuff. Well, it's not just the device size, the number of qubits that will dictate the size of the graph. But it's more importantly, the fidelity, coherence windows. How deep of circuits can we run? So what's interesting is that over the past few weeks, we've seen a number, I think it's 5 now, of announcements of different roadmaps for building bigger quantum computers. And I suppose that we can definitely say this is the NISC era represented on this map. So this is IBM's map. So they're claiming, they have an architecture and this roadmap here that takes them from where they are right now around, whatever, 27, 65 qubits, up to 1,000 by 2023. Also with the intention that around that time with that 1,000 qubit chip, they're going to be at a point there where they can use all those qubits to produce one error-corrected logical qubit. Okay. So there's a tension here. We're in the NISC era, and we might want to run QAOA on NIST devices and use all the qubits to represent the problem. So maybe you run 1,000 node graphs on this 1,000 qubit device. But it's likely that the coherence times will be woefully inadequate to run any instance of that size with the necessary circuit depth. So it's interesting to consider maybe, will we be able to do anything useful with QAOA on, let's say, their chip design, when it seems more like the intention is to arrive at an error-corrected qubit and then start scaling that up from there. And so interestingly, Google has the same, very similar roadmap and the same number, around 1,000 physical qubits. They want to be able to create one logical. So I think it's the same story here. And their technologies are very similar, superconducting transmon qubits. So all this makes it very challenging for this QAOA problem, for MaxCut and so forth. Another interesting announcement was from IonQ. This came out a few days ago, I think, last week. Is so they do trapped ions, and so their qubits are quote unquote perfect, not exactly, but they're all the same atom, and there's a lot less of the variability in you get in transmon qubits. But it also comes with a much longer gate times, so you have that trade-off. But they claim to have a really crazy large quantum volume. If anyone has been tracking this metric that is getting used, like IBM is claiming a doubling of their quantum volume, I think at least every 12 months, maybe every 8 months. And then Honeywell has reported their quantum volume, but these quantum volumes they've reported so far are like 64 and 128 maybe. But IonQ here is claiming that they achieved a quantum volume of 4 million, which basically corresponds to like 22 qubits operating more or less error corrected. So it doesn't mean they're perfect, but it is a very large number. I'll have to say it's a pretty big jump from where the other technologies are right now. But we're gonna need to see the release on the publication, all this. But so far, IonQ has been pretty transparent. So the other thing here is, so they have a similar plan. They want to double the size of their devices every 6 months or 8 months, I think was the quote. But the key here is that even with the longer gate times, if they can manage to scale these long coherence times up to devices in the 100 qubit, 150 qubit range, things get really interesting there. Maybe not necessarily for MaxCut, but for other problems like material science problems. Okay, yeah, another player here, but there's less information on them, is PsiQuantum. And they've raised a whole bunch of money so far, and they're working on really they're also doing the same thing, working on leapfrogging to the error corrected qubit architecture, where I think they're more focused on material science problems and hitting that 100 to 300 logical qubit count number. And then actually just today, Xanadu released yeah, that's right, yeah, the D-Wave also has their 5,000 qubit device out, where I think previous iterations suffered that even though they had maybe a 2,000 qubit device, it's not universal gate, it's only running annealing. And then it also suffered from the mapping where at the end of the day, you didn't get to realize, let's say 2,000 variables in your problem, you only got to realize 100 or something, or even less. And I think I heard something about this new device allows a better mapping and allows you to actually run pretty interesting problem sizes. So I'm definitely interested in doing benchmarks on this device myself, but don't know much more about it than that. So yeah, but the D-Wave, that's still an interesting player. But yeah, so I think if you aggregate, this IBM, Google, IonQ, PsiQuantum, Xanadu, you have something like some guarantee on like 1,000 qubits by 2023. Maybe IonQ can deliver on a number like that, but with very long coherence times. But it seems like, yeah, there's a major focus on getting to 1,000 to aggregate, so you make an error corrected qubit. And so, but all 5, I think, of these I just mentioned have a target for 1 million error corrected qubits by like 2030 or even less. And so, yeah, in terms of the whole narrative here, that's what I had planned to talk or to say. I wanted to mostly like maybe go back or answer questions because I didn't know exactly how to to frame the narrative. But it seemed natural to end or to show that basically the results of our work aren't going to be really conclusive until we have devices that are big enough, and maybe more importantly with coherence times long enough, that you can actually run, problems of a practical size. So until we get to that point, we're just waiting, I think is the point. And then I would say in maybe an aggregate as well is what maybe the crowd thinks of all this. By nodes, I need nodes in the graph, and then the number of nodes in the graph maps the number of qubits. So each qubit represents a node in the graph in this QAOA. Did I answer that question? What fidelity percentage is high quality? Okay, yeah, so Google's Sycamore, from what I understand, and it's hard to give a single number for fidelity because what you really need is like 1 and 2 qubit error rates. That's a much better indication of the quality of the device than just a single fidelity number. But what's often reported is a fidelity of like 0.9 or 0.99 or 0.999. What that means is that a 0.9 device has a 1 in 10 probability of incurring an error, basically. 0.99, 1 in 100, 0.999, 1 in 1,000. And the Sycamore, from what I understand, is a 0.994 device. And that was like what allowed it to just sort of do the supremacy demonstration. Like they needed that fidelity sort of threshold to be met, 0.994. From what I understand, I think IonQ's is effectively 0.999. It's 999, the device that claimed to have demonstrated a quantum volume of 4 million. So we should be, a good device right now is 0.99, 0.999, and we should expect that to be at least that good or better. We would want better than that, but how's that? Oh, any views on quantum memory? What are my views on it? Oh wait, I'll answer John's question in a minute. Views on quantum memory. Well, my views are that it'd be nice to have. It's required for a number of things, and yeah, but I don't have good views on it. Like I don't know where that technology is. I mean, actually, I guess you could say that Google and the rest of these manufacturers must be, they must be investigating these chips they're designing for the possible use as a quantum memory. But my understanding is that quantum memory implementations rely on fundamentally different technology than the transmons because you need memory to be more stable. But I'm not sure. In some sense, I would say that quantum memory is just like a quantum chip that has error correction implemented so that it can maintain a state and persist for some time. But I'm sorry, I don't have any better comments on that. John, I have a graph with 230,000 nodes. When will quantum help me? My bet on that would be not until we have fully error-corrected devices, and maybe not even then. It's definitely not going to help in the disk era. Yeah, and that 230,000 node, that's probably what, a Twitter data set, or it's something at scale. Yeah, I think within this space is more like a niche, it's like you have to hunt around for the advantage through these different graph types and so forth. And then you have to wait for the device to get bigger. Or you need to figure out a better way to represent the graph on the limited number of qubits you have. Represent a bigger graph than the number of qubits you have. But my guess is not until we're in the error correction era. At least 10 years, if that. Is this a good way to do it for me to say out loud what the answer is to these questions? Someone asked, but can't the fidelity be improved by adding noise using machine learning? How about instead of can the fidelity be improved, can we say, can the outcome of measurements be improved using machine learning? And that's certainly true. You can also improve the outcome of measurements by injecting controlled noise or in mitigating it. IBM has this technique. Yeah, there's a bunch of ways to. I mean, yeah, this is a whole focus. This is like an entire group at IBM, at Google, are working on that problem. Like really working with the noise, seeing if you can leverage it at all to improve the performance or any way to mitigate it before we can actively correct it. But then you also saw on the roadmap, they have a roadmap where they're all going after error correction by like 2023. So while people are trying their best to suppress noise and mitigate it, they're still going after error correction, active error correction. Like that's going to be the thing that actually solves the noise problem. Yeah, Reddit. Yeah. Yeah, no, I don't think you're going to be doing that. I mean, what might be the case is in some hybrid way, in a total graph analytics, workflow, there might be some portion of the graph or some particular operation you want to do on it that might be suited for a quantum computer. But for what you're doing with that Reddit thing and the 230,000 nodes, my best guess is not for 10 years at least, if then. Okay, those are good questions. Any more?
So, Jason,
Yep.
the classical algorithms you just mentioned, I could get the references in your paper?
Yep. Yeah,
Okay.
actually, one of the really great references. So yeah, the paper has a lot more references. If anyone has any questions about this and wants specific reference, something like that, you can email me. I don't know if I provided I think my contact information is available through like the meetup, registration thing. But there's a lot more references in the paper. And a particular reference I really like is this, the one that this plot comes from a paper called What Works Best When. And it's an analysis of like a whole bunch of heuristics for QAOA and MaxCut problems. So it's a great paper. And essentially you'd want to reproduce this paper on quantum hardware, I would say. That would be, and you need the real devices to do that. You can't just simulate all this stuff. So my idea would be like, you want to basically take this paper, what works best when, and make a quantum version of it. What works best when, the quantum version. And by the way, that would include D-Wave, right? Like you could expand this out and say, that paper plus D-Wave plus IonQ results plus the rest of the hardware,
Okay, thanks.
Sure. Is there any other 230 nodes? Yeah, D-Wave called their machine the quantum advantage. I'm not sure why they chose to do that. Oh, that's a good question. John, but what's the graph type on those 230 nodes? What's the structure of it? Does that answer varies significantly depending on the graph type? Give a range. Oh, okay. Here. Let's see on the screen. Is there any 230 nodes on there? Not quite that big. You have the PA road net. I think so this PA road net, it's pretty dense though. Edges. It really depends, man. It's hard to give a range. So how about this? Hey, John, ping me. Oh, we can talk about that tomorrow. I'll give you a better range. It's just really hard to do so because I'm thinking like there's at least 5 to 10 different graph types. The range ends up being something like, the range could be anywhere from minutes to days or never or that kind of thing. Okay. Are there funded PhDs at Carnegie Mellon in the quantum computing area? I think the answer to that is yes. It depends. Is what you're asking? Is there like advertisements for are there advertisements for positions right this moment? I don't know for sure. But that being said, there's several faculty that I could direct you to who are interested in, if they don't have funding right this minute for quantum computing, they're interested in pursuing it. And there's a lot of money coming in from the NSF and other, and DOE for quantum computing. So there might not be funding immediately available, but there's definitely interest, and I can let you know who those people are, if that helps. Okay, cool. Yeah, John. It is possible that you can solve graph sizes that big in like a pretty crazy short amount of time, like seconds, or not seconds, minutes, or it could take hours, days. Isn't D-Wave different in terms? Yes, D-Wave is not a universal gate quantum computer. It doesn't implement a universal gate set. It just does quantum annealing. So it only runs optimization. And actually, from what I understand, it basically just only does QAOA, which is what this MaxCut problem is. But MaxCut, D-Wave can do non-QAOA things too, from what I understand, but QAOA can also as well. But they're very similar. Okay, here, SK, here, you should send me an email or something like that, SK. I can give you more, I can give you the names you want. Let's see, what else? How do you, sorry, I didn't see that one. How do you translate a K-regular graph to the quantum circuit? Oh, okay. So the quantum circuit, it's defined by this variational form, and it's also defined here, but it's not so, it's not so clear what the circuit structure looks like just by reading this. But basically, the cost function is going to impose basically a C0, a 2-qubit gate between qubits, which are the nodes. So you have qubit 0, 1, whatever, and that's the same as it's representing, that qubit represents node 0, 1, so forth. Then this C operator, the cost function, and these Z operators are going to impose a C0 control NOT gate between nodes that have an edge connecting them. So if you see, I think I have it somewhere here. Basically, this graph here, you have nodes with the various edges connecting them, and then this pattern of C0 gates in the circuit has the same connectivity as the graph. Okay, and then you're going to also, if you map that to an all-to-all connected device, that's fine. There's no further scheduling necessary. But then if you have only a nearest neighbor connectivity, now there's some additional scheduling, some additional overhead swaps and so forth you might need to use. So it really depends on the hardware, but I think that answers your question. Let's see if there's anything else. Yeah, that's it so far. Okay. Anything else? Those are all good questions. And then SK, I can't see your name. Yeah, send me an email. I'll send you a list of faculty. There's a handful. It also depends on what the topic you're interested in, or actually doesn't matter that much. Anything in material science, combinatorial optimization, machine learning. Or I thought I wrote it to you. Type answer. I can put on the screen as well. Sorry about that. So I sent it in the Q&A. I'll go ahead and put it up on the chat here. Here we go.
Okay, Bikash, are you there? Hey, Bikash. Hello, Bikash? Oh,
What happened to him?
can you hear me?
Yep.
Okay, Bikash, are you there? I think he's not there. Anyway, thank you. Is everybody there? I don't know. So we'll end here.
Oh, now that I exited from full screen, I can just check the chat real quick and see if there's anything.
Oh,
Here, there's some other comments here. Let me just read these real quick. So someone mentioned, I think time dependency of the unitary operator in QAOA is critical for parallel quantum computing. By parallel quantum computing, you mean like quantum computing on multiple quantum chips? Or what is the meaning of this? Okay, so I'll ask that one. So I'm not quite sure what your definition of parallel quantum computing is. Someone says, I mean unit vector. Can you post a link to the recording and are slides available? Oh, that's another thing. How about I'll just send the slides to Deb and he can distribute to the group. Mark, yes, the recording, yep, will be available on YouTube. Sorry, I'm late.
Yeah, so we'll put the recording on Association Quantum's YouTube channel.
Good, okay. Oh, I see. There was some last question. Are we talking symmetric multiprocessing? And I'm not quite sure. Oh, I see. Yeah, quantum computing by default offers massive parallelism, isn't it? It is true in some sense, but I don't think completely in the sense that you're thinking about it. But sure, okay, good. Yeah, I know what you mean. Actually, we can talk more about that once you email me. And then that final question, are we talking symmetric multiprocessing? I don't remember what that was referring to. Oh. Are we talking symmetric multiprocessing parallel process where the program is broken up for more efficiency? Sure. Are you asking whether or not the algorithm, like the classical algorithms I showed you, had that? Whether or not they had parallelism implemented? For at least, although actually I don't recall myself running any particular instance in parallel, although there was parallelism, there's parallelism in, for the Gomez-Williamson SDP, semi-definite relaxation, you do so with some type of optimizer. And yeah, but the Python, the CDX opt implementation of Python, I'm pretty sure is multi-threaded. But actually, I recall myself not parallelizing over in threads over a given instance, but rather running single core instances across instances of the graph or instances of the problem solution. But yeah, there is parallelism here. And you can, yeah, maybe I should say, like, once these graphs, like if you wanted to solve a MaxCut really big graph, and it gets to, you know, like HPC petascales, then there's definitely, even the algorithms I discussed here, there's parallel versions of them that are implemented at scale. So, okay. Oh yeah, and making connection class with quantum. Yeah, yeah. So it's very important here that even like the benchmarks I showed you, that's not even the final word. You know, it's sort of, there's a bit of the moving goalpost aspect to this, which you brought up, which is like, well, all you showed me was like some single core results and parallelism over the instances. What if I have a really big one, you know, and I want to run, I need to throw all my computation at that really big instance. Then you're up at the scales that John was talking about in the chat, where he asked about 230,000 node instances. And it's like, I'm not sure when quantum will get there, those sizes. But yeah, there's definitely more parallelized versions of the stuff I've talked about, and at larger scales. The infrastructure would or might work towards moving like the SETI home project. Oh, okay. I'm not as familiar with that project, so I have to look into it. But the quantum and classical hardware is already heavily integrated. Like they're already heavily hybridized, and that's going to continue. Like you need classical is critical in error correction implementation, for example, and then just I/O. You know, like initializing, executing, measuring. Okay, how's that? Any more questions?
If not, thank you, Mr. Jason, Dr. Jason.
Sure.
And hope you'll come back again.
Hit me up the next time I have a paper.
Yeah. Next time you'll have people will let me know, and I will have another session with you. And thank you all for coming.